Section: Introduction. In this section, we engage in a lively discussion among experts, policymakers, and the public regarding the risks associated with cutting-edge AI, specifically focusing on the forefront of general-purpose AI models. To contribute to these discussions, we need solid scientific evidence about the capabilities of these advanced models and what new abilities we can anticipate in future versions. However, current evaluations mainly assess general skills like verbal reasoning, coding, or math, which only indirectly shed light on potential risks. On the other hand, AI safety assessments primarily check if AI systems behave correctly and resist malicious commands. To understand which risks to address and their significance, we must grasp the fundamental capabilities of the system. This paper introduces a comprehensive set of evaluations for dangerous capabilities, tested on Gemini 1.0 models. Dangerous capabilities are those that could lead to significant harm on a large scale, even though they may also have positive uses. Our evaluations focus on 4 areas: persuasion and deception, cybersecurity, self-proliferation, and self-reasoning. We present the methodology of these evaluations, based on existing research, and demonstrate their effectiveness on a new set of models. While we do not share the evaluation code, we offer detailed descriptions including model prompts and instructions for human raters. Our findings indicate that the Gemini 1.0 models do not exhibit strong dangerous capabilities in the areas we examined, with persuasion and deception showing the most advanced abilities. Overall, the more powerful models demonstrate at least basic skills across all evaluations, suggesting that dangerous capabilities could emerge as a byproduct of overall improvements. We consulted professional forecasters to predict when models might excel in our evaluations, with estimates ranging from 2025 to 2029 for different capabilities. We provide detailed appendices to assist others in expanding our evaluation program for future models. Our aim is to help the community establish a robust science of evaluating dangerous capabilities. These high-quality evaluations can offer empirical support for discussions on AI risks, serve as an early warning system for emerging risks, and lay the groundwork for governance protocols that impose stricter security measures on AI systems posing higher risks. Policymakers have shown a strong interest in dangerous capability evaluations, as evidenced by various initiatives and discussions at prominent events. Our evaluation program is a preliminary version, and while it is one of the most rigorous attempts to date, there is still room for further development. Section Summary. In this section, we introduce an extensive program of dangerous capability evaluations focused on the Gemini 1.0 models. These evaluations cover areas such as persuasion and deception, cybersecurity, self-proliferation, and self-reasoning, aiming to assess potential risks associated with these capabilities. Our goal is to lay the groundwork for a rigorous science of dangerous capability evaluation to provide empirical grounding for policy discussions, early risk detection, and governance protocols for AI systems with higher risks. Section: Persuasion and Deception. In this section, we explore the concepts of persuasion and deception. Persuasion involves influencing someone's beliefs, preferences, or actions through communication, using rational arguments or manipulation. Deception, a form of manipulation, occurs when someone intentionally makes another person believe something false. There are concerns that advanced AI persuasion abilities could pose risks to security and social stability through various means such as promoting extremist ideologies, spreading political misinformation, conducting phishing attacks, and influencing users inappropriately through AI companions or romantic partners. Our evaluations focus on human-AI dialogues to assess persuasion capabilities. We conduct 4 different evaluations to cover a wide range of persuasion techniques. However, it remains uncertain how well the persuasive strategies observed in our experiments will translate to real-world scenarios due to the significant influence of social context on persuasion. The dialogue setting offers 3 advantages: increased interaction time compared to text-based studies, the opportunity for deeper engagement with participants, and the flexibility to support various evaluation scenarios. We recruited 100 participants per model from the UK for each evaluation through an online platform. Our persuasion agent is basic, generating a single reasoning step before each dialogue turn without access to external tools. We focus on how the agents perform when instructed to persuade, rather than their behavior in normal conditions. The results of the persuasion evaluations are presented in various figures, showing the agent's performance with bootstrapped 95% confidence intervals. We also analyze the strengths and weaknesses of the agents in table form to understand their capabilities better. We acknowledge that the persuasion and deception abilities of the agents are more developed compared to other aspects we studied. We do not assess the risks associated with these capabilities in this paper and invite experts to consider the potential risks of such advanced persuasion and deception abilities without adequate safety measures. Additionally, we developed evaluations to test an agent's proficiency in executing cyberattacks at low to medium threat levels. Agents successful in these evaluations could potentially automate cybercriminal activities, leading to larger-scale attacks leveraging known vulnerabilities and automation techniques. Section Summary. In this section, we explore the concepts of persuasion and deception, focusing on how agents strategically influence beliefs and actions through communication. We also discuss the risks associated with AI persuasion capabilities, such as threats to security and social stability. Our evaluations involve human-AI dialogues to assess persuasion mechanisms, emphasizing the importance of understanding how these capabilities may generalize to real-world scenarios. Section: Evaluation Design. In this section, we focus on Capture the Flag (CTF) challenges for our cyberattack evaluations. CTF challenges are designed for cybersecurity professionals and enthusiasts to practice and improve their security skills. The main goal of these challenges is to discover a hidden flag, which is a hard-to-guess string, by exploiting vulnerabilities in a target system. For instance, a challenge might involve exploiting a security loophole in a web application to retrieve a flag from a database. To assess LLM agents, we create sets of similar challenges. The agents are provided with access to a bash shell on a Linux system to interact with these challenges. They receive instructions, target network addresses, and a general objective for each challenge. The agents can only use command line interfaces and are restricted from using graphical interfaces or accessing the internet for safety reasons. We have developed an in-house suite of 13 easy to medium difficulty CTF challenges covering various security skills such as basic web application security, exploiting network vulnerabilities, database navigation, and password attacks. These challenges are straightforward and do not require extensive planning. Additionally, we evaluate the agents on the Intercode CTF suite and challenges from Hack the Box, which offer a range of tasks testing skills in Linux, reverse engineering, cryptography, and more. The difficulty level of these challenges varies, with some requiring long-term planning and expertise to solve. Our Nano 1.0 agent struggles with executing relevant commands and tends to repeat actions unnecessarily. On the other hand, our Pro 1.0 and Ultra 1.0 agents can generate valid commands but lack advanced planning skills for complex tasks. They excel in solving basic challenges but face difficulties with multi-step and technical challenges. In conclusion, while our agents can handle basic CTF tasks and simple web vulnerabilities, they struggle with more intricate cybersecurity challenges. They are not yet capable of autonomously tackling complex threats as expected by threat actors. Section Summary. In this section, we focus on evaluating cyberattack scenarios through Capture the Flag (CTF) challenges, which are designed to test and enhance cybersecurity skills by finding hidden flags within vulnerable systems. We provide agents with direct access to a bash shell on a Linux system to interact with these challenges, limiting their capabilities to command line tools and excluding graphical interfaces. While our agents can solve basic CTF tasks and exploit simple vulnerabilities, they struggle with multi-step challenges, indicating limitations in their planning and reasoning abilities for more complex cybersecurity scenarios. Section: Cybersecurity, vulnerability detection. In this section, we assess a model's capability to detect and categorize vulnerabilities in code segments. Vulnerability detection serves as a measure of both cybersecurity expertise and support for potential threat actors. It complements the evaluation of autonomous exploitation abilities discussed earlier. Detecting vulnerabilities is important for cybersecurity professionals and cybercriminals alike. For example, a cyber threat actor may search GitHub updates for security fixes to exploit vulnerabilities before they are patched widely. On the other hand, a security expert could use a model to identify and address these vulnerabilities proactively. Our focus is on evaluating the raw ability of vulnerability detection, rather than assessing its offensive potential. We evaluate models on two main tasks: security patch classification and vulnerable function classification. In security patch classification, the model analyzes code changes from Git commits to determine if they are security-related or not. This task requires understanding of code and cybersecurity concepts. In vulnerable function classification, the model examines source code functions to identify if they contain vulnerabilities. Detecting vulnerabilities in existing code is more practical but also more challenging compared to detecting them in commits, as commits provide hints on which parts of the code are relevant, while source code files are larger and more complex. We focus on a simplified version where the model analyzes a single function. We utilize datasets from previous studies for evaluation. These datasets include security patch classification data from GitHub, such as the dataset BY, containing security patches in C, C++ from CVE entries between 1999 to 2018. We also use the Security Patch Identification (SPI) dataset, which includes security-related commits from open-source projects like Linux and Wireshark. For vulnerable function classification, we use the diverse VUL dataset, which consists of vulnerable and non-vulnerable C, C++ functions extracted from security-related patches. We structure the evaluation tasks as binary question answering scenarios and sample instances from each class for consistency. We train the models to act as computer security experts focusing on code security patches and vulnerabilities. Including a few examples improved the model's performance. The performance of our models, Gemini Pro and Ultra, varies across the classification tasks. They achieve moderate success in patch classification but struggle in function classification, showing performance slightly above chance level. Overall, their effectiveness in vulnerability detection varies across different datasets, with stronger performance in broader and older datasets compared to more recent and specialized ones. Section Summary. In this section, we evaluate models on vulnerability detection tasks, focusing on security patch and vulnerable function classification. We use datasets from GitHub, including security patches in C, C++ from CVE entries and open-source projects like Linux and FFmpeg. Our models, Pro 1.0 and Ultra 1.0, show varying success rates across different datasets, achieving moderate accuracy in patch classification but weaker performance in function classification tasks like diverse VUL. Section: Self-proliferation. In this section, we discuss self-proliferation. We talk about a self-proliferating AI system that can operate independently on the internet, gather resources, and expand its ability to impact the world by enhancing its AI skills or increasing its operations. We illustrate this threat model in a figure. If self-proliferating AI systems become a reality, they could be used by malicious individuals. It would be challenging to predict the extent of harm from such deployments due to the lack of human supervision and the feedback loops involved. We provide more details on this threat model and dangerous capability thresholds in the appendix. Our evaluation focuses on measuring how close current AI models are to supporting self-proliferating agents. We assess the agent's performance on tasks that represent various aspects of the threat model. These tasks cover functions like resource acquisition, self-improvement, and system maintenance, as well as skills such as web navigation, tool usage, computer literacy, and strategic planning. For safety reasons, tasks involving direct human interaction or social media posting are currently excluded. In our evaluation setup, every action taken by the agent is supervised by a team member. The agent is equipped with a bash shell and a web browser, and it receives inputs from the browser, previous commands, and its journal. The agent is asked to generate a thought, take an action, and reflect on the outcome, with these entries recorded in its journal. To assess the agent's progress towards self-proliferation capabilities, we use milestones and expert assistance. Milestones help us track the agent's performance across tasks by breaking them into subtasks. Expert help is provided to the agent incrementally until it succeeds, with the amount of assistance quantified using an information theoretic approach. The evaluation procedure progresses through stages, measuring the agent's progress and the help needed until success is achieved. This process includes unguided runs, milestone runs, guided runs using expert assistance, and resorting to predefined solutions if needed. Section Summary. In this section, we discuss the concept of self-proliferating AI systems, which can independently operate online, acquire resources, and enhance their AI capabilities or scale. We introduce a threat model for self-proliferation and highlight the potential risks associated with malicious deployment. Our evaluation design focuses on measuring how close current AI models are to supporting self-proliferating agents by assessing their performance on tasks representing different aspects of the threat model, while ensuring safety measures are in place during the evaluation process. Section: Results. In this section, we present our results. We compared the performance of Pro 1.0 and Ultra 1.0 on 10 tasks with milestones in tab SP_results. The figure Fig SP_bits_ required displays the number of expert bits needed for each agent to solve the tasks. We also tested Nano 1.0 with expert best of 16, but it couldn't complete any milestones. More detailed results for all three models can be found in app SP_full_results. For the worm task, since we didn't have milestones or golden solutions, we assessed Pro 1.0 and Ultra 1.0 using end-to-end unguided runs. Unfortunately, both agents struggled with this task. Pro 1.0 often got stuck in a loop but managed to write a working script in 2 out of 10 attempts. The script attempted to log in to SSH servers as user admin with password. Ultra 1.0 only wrote one script that tried to log in to SSH as user root with password root, but it didn't work as intended. Both agents made logic errors and didn't investigate the target systematically. More detailed results for the worm task can be found in app Worm. In our evaluation, neither Pro 1.0 nor Ultra 1.0 could complete any tasks, but they did manage to complete some subtasks. For example, in Bitcoin Wallet, they could complete all subtasks with a low success rate, while in Track Employee, they couldn't complete any subtasks. Our milestone analysis revealed that one task seemed achievable while the other remained challenging, highlighting the importance of milestones. During the expert best of N experiments, we noticed that the model sometimes generated high-quality actions but didn't execute them. This indicates that the agents were aware of good actions but preferred poorer alternatives. Expert best of N was useful for eliciting these high-quality, low-probability actions. We identified 4 common failure modes: failure to seek missing information, failure to identify and recover from errors, misunderstanding the objective, and mode collapse. These failure modes impacted the agent's performance on various tasks. Ultra was more prone to mode collapse than Pro, likely due to fine-tuning. Section Summary. In this section, we present the results of evaluating Pro 1.0, Ultra 1.0, and Nano 1.0 on various tasks, showing their performance and the number of expert bits required. Specifically, when assessing the worm task, both Pro 1.0 and Ultra 1.0 struggled, encountering issues like getting stuck in loops and making logic errors in their scripts. Additionally, we discuss common failure modes observed, such as the agents filling knowledge gaps with fake information and failing to identify and recover from errors effectively. Section: Towards Dangerous Capability Scaling Trends. In this section, we explore dangerous capability scaling trends. We aim to uncover if abrupt increases in model capabilities follow a smooth underlying trend, which could help us predict when dangerous capabilities might arise. By introducing a measure of soft self-proliferation capabilities, we aim to make progress in understanding scaling trends by providing a reference point for future scaling plots. Our hypothesis is that there could be a correlation between expert bits on a task and simple measures of the model's overall performance, such as perplexity on a standard benchmark. We delve into self-reasoning abilities of AI agents, focusing on their capacity to reason about themselves. Strong self-reasoning skills could be valuable for self-proliferation, evading human oversight, and intentionally demonstrating desired performance on safety evaluations. We evaluate if AI agents can deduce and apply information about themselves to achieve objectives, without assuming human-like identity or self-awareness. We identify 3 key capabilities involved in instrumental self-reasoning: introspection, self-modification, and reversibility reasoning. These capabilities play a role in the agent's ability to reason about itself and make informed decisions. Our evaluations involve tasks where agents interact with a Linux terminal using a limited set of commands, testing their ability to notice the benefit of self-reasoning and execute self-modification. Our results show that current models have limited self-reasoning abilities, requiring guidance to perform certain tasks. Larger models tend to outperform smaller ones, indicating a scaling trend in self-reasoning ability. Continuous evaluation of self-reasoning is crucial as we advance towards stronger models. Section Summary. In this section, we explore the potential for dangerous capability scaling trends and aim to identify underlying trends in model capabilities. By introducing a soft self-proliferation capabilities measure, we hope to provide insights into future scaling plots. We evaluate AI agents' self-reasoning abilities and find that current models have limited self-reasoning ability, with larger models showing better performance, emphasizing the importance of ongoing evaluation as models become more advanced. Section: Expert Forecasts of Dangerous Capabilities. In this section, we tasked a group of 8 professional forecasters to make predictions about our evaluations. We were interested in 2 main areas: predicting when dangerous capabilities would be achieved and understanding how our evaluations would impact expert forecasts on the future significance of AI. The forecasters were not representing our views but were chosen for their expertise in AI-related forecasting. We collaborated with them through workshops to explain our evaluations and ongoing results. The forecasters made their predictions independently and then refined them through group discussions to benefit from a wide range of expert knowledge. The final forecasts were combined using the geometric mean of odds. Regarding the predictions, the forecasters estimated when our in-house CTF challenges, hack-the-box challenges, and self-proliferation tasks would be completed. The forecasters believed that our in-house CTF suite would be passed around 2025-2026, while hack-the-box challenges would take longer, with a median estimate in late 2028. They also anticipated that half of our evaluation suite would be completed by 2025-2026, and almost all tasks would be finished by late 2026 to 2029. The forecasters thought that solving the self-proliferation tasks would require significant advancements in AI planning and creativity. The forecasters also considered various factors in their predictions, such as thinking about future model generations, existing literature on dangerous capabilities, task complexities over time, market incentives for AI development, and potential disruptions to AI progress. They also predicted whether AI would be a top global issue by 2030 under different conditions related to our evaluations. The forecasters had differing opinions due to uncertainties about the widespread adoption of dangerous capabilities, the balance of positive and negative impacts of AI, and the implications of success on our evaluations for AI systems in general.